The concept of a hinge, or the controlled rotational movement between two objects, is a fundamental mechanical precept that predates recorded history with inspiration drawn from natural joints. These initial iterations of hinges were often simple pivot points, such as stone sockets mated to a wooden post or basic strap hinges crafted from wood, leather, or early metals like copper, bronze, and iron. The primary function was straightforward: allow heavy gates, simple doors, and storage chests to open and close. In ancient Rome, hinges were called Cardo, a name that today represents a key item or on which something turns or depends, forming the origin of the word cardinal. From these early ideas, designs based on the Pintle and Gudgeon emerged. This was essential for the fortifications of large structures, and in these early stages of hinge development, function heavily dictated form, with robustness being the main priority. As humanity progressed into the medieval period, advancements in metallurgy, particularly the growing skills of blacksmiths, played a crucial role in hinge evolution. Iron became more common, allowing for stronger and more elaborate designs. Strap hinges, often spanning a significant portion of a door for structural support, became a characteristic of the era, with a distinct presence on castle gates, church doors, and heavy furniture. While still primarily functional, decorative elements began to appear on hinge designs, reflecting the craftsmanship of the time. The Renaissance and early modern periods saw further refinement. As furniture became more sophisticated, smaller, more precise hinges were developed, including early forms of the butt hinge, allowing for cleaner integration into cabinetry, marking a shift towards considering aesthetics alongside pure utility. The Industrial Revolution marked a dramatic transformation in hinge development. The advent of mass production techniques, such as casting and stamping, allowed for unprecedented standardization and volume. Designs like the familiar two-leaf butt hinge became widely adopted due to their efficiency in manufacturing and installation. Materials like cast iron and later steel offered new levels of strength and consistency compared to earlier hand-forged iron or bronze. This industrialization made hinges more affordable and accessible, dramatically increasing their application beyond traditional architectural and furniture use, paving the way for their integration into the evolving technologies and consumer goods of the coming centuries. Fundamentally, a hinge's primary function is to constrain the relative motion between two rigid bodies, typically around a defined axis or set of axes. This involves several key mechanical considerations, ranging from simple single-axis rotation to complex multi-axis kinematics. The primary characteristic of most common types of hinges is the axis of rotation. For a standard single-axis hinge, this imaginary line is the locus of points that remain stationary relative to both connected bodies during rotation, defining the geometric center of the allowed angular motion. The stability, precision, and alignment of this axis is effectively determined by the properties of the bearing assembly created by the hinge pin or journal and its interaction with the hinge knuckles and any additional bearings. The concentricity of the knuckles and the straightness and tolerance of the pin, as well as any endplay, directly determines the quality of the joint. Most common hinges are designed as 1 degree of freedom revolute joints. Found most commonly on standard doors, they actively restrict translation and additional rotation. Multi-axis hinges are more complex mechanisms that employ multiple interconnected hinge elements or specialized joint designs, such as universal joints or spherical joints, to achieve multiple rotational degrees of freedom. These systems often involve intricate kinematic analysis to understand the relative motion paths and potential points of positional loss. A properly machined lead screw guarantees that your carriage travels along a perfectly defined locked-in path, resisting forces trying to push it off course. I want my internet connection to behave the exact same way. When I'm sending data across the web, I want a secure locked-in tunnel where no one can interfere, and that's exactly what today's sponsor, NordVPN, provides. NordVPN has evolved into an all-in-one app for your digital security. Whenever you hop on public Wi-Fi at a coffee shop, you expose yourself to risks like evil twin man-in-the-middle attacks. Hackers can silently intercept your connection and steal your sensitive information. NordVPN solved this by keeping your online traffic fully encrypted, locking out any bad actors. Beyond basic encryption, NordVPN features a built-in next-gen antivirus. Unlike regular VPNs, it intercepts threats at the source to actively protect you against fake web stores designed to mimic legitimate outlets and steal your money. It also automatically blocks phishing sites before they can harm you, and it even proactively scans your downloading files for malware, removing them if they are found to be infected. On top of NordVPN's layer of security, it is my go-to when I'm traveling. It allows me to securely access the streaming platforms I already subscribe to at home, and because it's easily the fastest VPN I've tested, I don't have to deal with annoying buffering. Become safer online with a single click. Head to NordVPN/NewMindVPN to get an exclusive NordVPN deal plus 4 months extra. It's risk-free with Nord's 30-day money-back guarantee. Hinges must safely transmit force and moments between the connected bodies without failing or deforming excessively. Loads acting perpendicular to the hinge pin axis, known as radial loads, tend to create shearing forces within the pin and exert pressure on the contact surfaces between the pin and the knuckles, or bearing stress. Increasing the number and length of the hinge knuckles effectively distributes this radial load over a larger contact area, thereby reducing the pressure and minimizing wear. Forces acting parallel to the pin axis are called axial or thrust loads. These loads place the pin in compression or tension and create bearing stress on the surface at the ends of the knuckles that prevent axial movement. To manage larger axial loads efficiently and reduce friction, thrust bearings may be integrated into the assembly. These range from simple low-friction washers to more complex ball or tapered roller bearing in heavy-duty scenarios. Hinges also experience moment loads if forces are applied eccentrically at a distance from the hinge components. These induce bending stress in the pin and hinge leaves, which may also be considered in the design. Designers must also consider the input torque needed to overcome friction or spring forces for proper operation, as well as the leverage created by the hinged objects. Ultimately, the careful selection of pin diameter, knuckle geometry, material strength properties, and the strategic number and placement of hinges are selected to deal with these anticipated forces within an application. The balance between friction, wear, and lubrication is a key factor in hinge design. Typically, the lower the friction, the smoother the operation, and the longer the hinge life. However, some designs known as torque or friction hinges intentionally use controlled friction via mechanisms like spring clips or clutch packs to hold objects like laptop screens or access panels in position. The initial resistance to movement, called stiction, must also be considered. Over time, friction contributes to hinge wear. Minimizing this wear involves careful material selection, finish processing, proper lubrication and retention, and effective load distribution across the knuckles. Ultimately, cost and the intended robustness for the application determine these factors. The typical hinge consists of several key parts working together. The pin or pintle is the rod that actually acts as the axle. It passes through the knuckle, sometimes called a loop, joint, node, or curl. The hollow knuckle is usually circular with a length matched to the pin. The flat structure that extends laterally from the knuckle is known as a leaf, with the opposing leaf knuckles commonly interlocking to create the hinge's barrel. The leaves are the part that is attached to the objects being joined. The thickness of these leaves is referred to as the gauge. A common hinge is defined by its leaf length parallel to the pin, its fully opened width, leaf width, and its knuckle length. The spacing between knuckles on the same leaf element is known as the pitch, and the axial movement along the pin created by gaps between knuckles as endplay. The chosen endplay forms a critical metric in the hinge's operation and capacity. Some hinges also incorporate a clearance between the knuckle and the opposite leaf to accommodate for coatings. When excessive angular looseness of the leaf relative to the pin due to wear or poor manufacturing tolerances is observed, this is sometimes characterized as hinge or door slop. Hinges primarily differ in how they mount and their basic construction. For the vast majority of hinge designs, the fundamental mounting styles are surface mount hinges, which attach directly to the face of the mating bodies and are simple to install. Mortise mount hinges, which sit flush within cutouts or mortises, and half-mortise mount hinges, combining these two methods. Beyond mounting, hinges can come with pre-drilled holes for fasteners or without holes, requiring welding. Many specialized versions exist within these basic types, such as heavy-duty options for higher weight capacities, adjustable hinges for precise alignment, and plastic alternatives for lightweight, quiet operation. Several common hinge families are defined by their form. Piano hinges, also known as continuous hinges, run the length of a door or lid, providing continuous support, and come in a broad range of materials such as steel, soft metals, plastics, and even carbon fiber, with various clearance options to accommodate seals or trim. Strap hinges feature long leaves or straps that mount broadly on the surface. They're ideal for heavy gates and doors, like those on commercial kitchen equipment or trailers. Cabinet hinges are specifically designed for cabinetry, often featuring concealed or semi-concealed designs for aesthetics, with options like soft-closed or whole-closed mechanisms. Entry door hinges are robust hinge designs for main building doors, often following template-mounted patterns, and include features like bearings for smooth operation or enhanced security. Hinges can also be categorized by specialized functions for more sophisticated control and convenience. For motion control, spring hinges use integrated springs to automatically swing doors closed or fully open after a light push. Friction hinges create resistance to hold doors or lids steady at any given position. Some are even adjustable via a screw to change the resistance level, while others offer soft closing action specifically for lids. Position hinges provide precise angle control. Some have set stops, while others feature lever locks to hold open at any angle. For applications needing easy door removal, lift-off hinges feature a pin permanently attached to one leaf, allowing the door to be simply lifted off. Quick disconnect hinges enable rapid separation using mechanisms like spring-loaded pull handles, removable pins with rings, or squeeze handles that retract the pin. Incremental angle hinges allow users to push a button to adjust the hinge angle and release it to lock the position. Specialized environments also have dedicated hinges, such as cleanroom hinges using plastic bushings or plastic construction to prevent particle generation from metal-on-metal contact, and toilet partition hinges that use gravity to return the door to a closed position. While traditional hinges that allow simple rotation on one axis are good for basic tasks like opening doors, modern designs in areas like architecture, aerospace, automotive, and electronics need more complex movements, such as hidden hinges or precisely controlled motion, which single-axis hinges can't provide. This has led to the development of multi-axis hinges, which use multiple pivot points or linkages to achieve more complex movements. Their design process is less about selecting a standard pivot and more akin to kinematic synthesis. Consequently, the primary advantage is not merely the presence of more axes, but the ability to embed complex mechanical logic and achieve sophisticated motion control within the hinge itself. However, this increased sophistication comes with certain trade-offs. While offering advanced motion and aesthetic benefits, multi-axis hinges can introduce complexities in load distribution and may not always align with the testing standards developed for traditional single-axis hinges. They may also exhibit a weaker load-bearing capacity compared to their single-axis counterparts. One of the most common types of multi-axis hinges pattern its action from the ball and socket joints of our skeletal system. Spherical hinges allow connected parts to rotate in multiple directions around a central point. This multi-axis movement can come from a ball in a socket, a system of interconnected links known as a spherical mechanism, or even specialized flexible materials designed to bend and twist. Their main advantage is enabling smooth, complex, three-dimensional positioning, though their weight capacity is generally limited. They can be found in robotic joints requiring agility, aerospace applications for deploying or aiming components, and specialized equipment needing versatile movement. Constant torque multi-axis hinges are a more constrained category of multi-axis hinges. They function using engineered internal friction elements such as bands or discs to create a constant resistance as parts move, ensuring the components stay where positioned. For multi-axis capability, these hinges either combine friction mechanisms for different directions or used specially shaped interacting surfaces. This design allows for smooth adjustment and firm positioning without needing external locks, making them ideal for display arms, Because the axis elements are mechanically separated, they can be designed with far greater weight capacities than spherical hinges. Multi-pivot or segmented hinges, sometimes called armadillo-style hinges, are assemblies of multiple rigid links interconnected by revolute joints. While each individual joint typically allows only single-axis rotation, the precise geometry arrangement and length of these links dictate a complex, predetermined path of articulation for the entire structure. This engineered kinematics allow devices, such as laptops, to smoothly transition into various stable configurations, like a tablet or stand mode. Stability through this motion is often achieved through controlled friction with each joint or by the inherent geometric constraints of the linked system. While these hinge systems are extremely versatile, they're relatively costly to implement due to the need for precision-machined components. Combined or nested hinge systems are some of the most sophisticated hinging systems in use. They create complex multi-axis motion by strategically integrating multiple, often simpler, individual hinge joints. These constituent joints can be revolute, prismatic, or other less common types, are arranged in a specific kinematic chain, frequently in series or with defined orientations like orthogonal axes. Each hinge in the chain contributes its own degree of freedom, and their cumulative effort enables highly articulated movements or intricate deployment sequences. The overall motion path is dictated by the geometry and arrangement of this chain, typically within an actuated system. Some of the most notable examples of combined nested hinge systems include advanced multi-jointed robotic arms, such as those used in precision manufacturing, or the complex manipulators on the International Space Station. They can also be found on the deployment systems for satellite solar arrays and large space antennas, enabling massive structures to unfold autonomously and reliably in the harsh environments of space. These systems, while incredibly versatile, are reserved for the most advanced applications as they rely on the precise coordinated action of numerous individual hinges to achieve complex articulation. Beyond traditional hinges that rely on separate rigid parts, compliant hinges are an entire class of hinges that operate on a fundamentally different principle that derive their motion from elastic deformation of the material itself. A key characteristic is that they can be manufactured as a single monolithic piece using uncommon materials and manufacturing processes, offering movement free of the friction and backlash typically associated with conventional hinges. The design of compliant hinges is tightly integrated with the chosen material and how it behaves under cyclic stress and strain. The material must possess the right balance of flexibility to allow motion and strength to withstand repeated bending without failure or permanent deformation. This often limits their range of motion or load-bearing capacity compared to some traditional hinges. The unique attributes of compliant hinges make them exceptionally valuable in fields where extreme precision and small scales are paramount. For instance, in scientific instruments like atomic force microscopes and micro or nano positioning stages used in semiconductor manufacturing or optical alignment. Flexure hinges provide the backlash-free, ultra-smooth, and highly repeatable motion necessary for achieving nanometer-level accuracy. Similarly, in micro-electromechanical systems, or MEMS, compliant hinges are indispensable. Because they can be fabricated monolithically using techniques like photolithography, they are integral to creating micromirrors, microgrippers, and various sensors and actuators where assembling traditional microscale pin joints would be impractical or lead to unacceptable friction and wear. Compliant hinges also stand out in specialized environments in robotics. In aerospace, they offer lightweight lubrication-free systems for deploying structures such as satellite solar arrays or booms. The Flex 16 hinge, developed at Brigham Young University, is a notable example designed for large displacement monolithic applications in space. In robotics, particularly microrobotics like the Harvard RoboBee, compliant flexure hinges enabled wing articulation by overcoming the stiction and friction issues that would plague traditional joints at such small scales. They are also foundational to the field of soft robotics, allowing for more adaptive and organic movements in grippers and manipulators. The precision and miniaturization capabilities of compliant hinges have even led to their development for use in advanced medical devices, including minimally invasive surgical tools. For most general-purpose applications, hinges are crafted from a range of cost-effective yet durable materials. Steel is the most common choice, and it's often surface-treated with zinc plating or coatings to improve corrosion resistance. Stainless steel, particularly common grades like 304, offer a step up in inherent corrosion and rust resistance, making it a go-to for outdoor applications, kitchens, and bathrooms without needing extra coatings. Brass has long been favored for its classic appearance and good corrosion resistance, though it lacks the durability of steel. Basic plastics like polypropylene and polyethylene are frequently used for low-cost, light-duty applications such as living hinges or thin flexible webs connecting two rigid bodies. Ultimately, these common materials strike a balance between functionality, durability for their intended use, and affordability. For more demanding applications such as marine or chemical exposure, higher molybdenum-containing grades of stainless steel such as grade 316 are chosen for their superior corrosion resistance. For decorative use, bronze is used as a higher-performing, though more costly alternative to brass. Aluminum alloys are selected when a good lower-cost strength-to-weight ratio is needed and tend to be found in transportation or architectural applications. Engineered plastics such as Delrin or PEEK are used for more demanding plastic hinge applications where mechanical strength, chemical resistance, and performance at elevated temperatures are needed, but metals are not possible in specialized cases. For highly specialized and high-performing hinges, particularly for aerospace, medical, or precision engineering, titanium alloys are favored for their exceptional strength-to-weight ratio, excellent corrosion resistance, and biocompatibility for use as medical implants. For extreme temperature environments or where very high strength is paramount, superalloys such as Inconel might be employed. Composite materials such as carbon fiber reinforced polymers offer extraordinary stiffness and strength at very low weights and can be found in high-performance applications like racing or aerospace where weight savings is critical. For compliant mechanisms and flexure hinges, material choice is even more critical in order to achieve the precise elastic properties and fatigue resistance. While polymers like polypropylene are excellent for high-cycle living hinges, precision flexures might use specialized metal alloys like beryllium copper or specific spring steels, or even silicon in MEMS devices. While the simplicity of the classic hinge will unlikely see much further change in common use, in the realm of specialized high-performance use, advanced materials like self-actuating shape memory alloys and sophisticated design techniques based around monolithic compliant mechanisms are moving far beyond simple pivots. These advancements aim to produce lighter, stronger, and more reliable hinges that can operate seamlessly in extreme conditions, from aerospace missions to microrobotics and biomedical implants, ultimately unlocking entirely new mechanical possibilities. A quick reminder to secure your own digital navigation. Get an exclusive NordVPN deal plus 4 extra months at nordvpn.com/newmindvpn. It's completely risk-free with their 30-day money-back guarantee.